Hello and welcome to the video lecture series brought to you by St. Andrews Institute of Technology and Management. My name is Ravinder. I am an assistant professor with the TCE department and we are discussing the subject called Data Structures 2 or Advanced Data Structures. And today we are going to see our last sorting algorithm for Unit 2, that is tournament sort. The tournament sort is just a simple application of your heap or your heapify method. Now, in the last lecture, we have discussed the heap sort. And in that heap sort, we have discussed how max heap could be used for sorting algorithm. Now, we have also discussed for a brief time what is minimum heap. Now, in minimum heap, the minimum element of the parent and the two childs will get to the top. Okay. While in max heap, as you have already know, the maximum value element of the parent and the two childs will get to the top or get to the root node. Okay, so tournament sort is actually an application of min heap. So let's move ahead. Now tournament sort is sometimes called tree sort or minimum tree sort. Okay, or tournament tree. Now we will sort this particular array, which is actually 2, 4, 6, 10, 1, 7, 3, and 8. Okay. Now for sorting, we will use a binary tree. Now, as you can see, all the elements of the array to be sorted are first inserted to the leaf nodes of the binary tree. So, uh, by as we have already discussed in the unit of trees, if you know the number of leaf nodes in a binary tree, or we can say in a complete binary tree, let me again tell you. For as we know that in the heap sort, in this case also we'll use the complete binary tree. So if you have a complete binary tree, the number of leaves in a complete binary tree, you can uh, figure out the total number of nodes in a complete binary tree, and by that you can actually decide what would be the length of the array which is going to be used for the implementation of that complete binary tree. So if you know the number of leaves, the total number of leaves in a complete binary tree, you can always decide by the use of the formula what would be the total number of nodes in the complete binary tree, and and in that what would be the total length of the array which is we are going to use for the implementation of this complete binary tree. Okay, so let's move ahead. Now, as with the rule of your minimum heap, that is min heap, you can see here in this subtree we have a parent, we have a left child, and then we have a right child. Okay, now at first all the leaf nodes will be filled with the array to be sorted out, and all the other nodes will be marked as either 1 or 0. You can, okay, you can see here I have marked them with numbers, but initially all these parent nodes or the non-leaf nodes including the root node will be marked as 0, will have the value as 0 or 1. Which one? 0 would be fine, I think. Okay, now we have a task here to fill those non-leaf nodes with the values. Now, how do we are going to do that? How we are going to decide which value is to be filled? Let me say this is we have to imply the formula of minimum heap. We have to imply the idea of minimum heap. In minimum heap, we have to decide between what would be the minimum value in the left child, the right child, and the parent. Okay, in this case, we don't have a parent here. It is essentially 0 at the beginning. So we have to decide which one of these two childs is smaller in value. In this case, as you can see, the value 2, that is the left child, is actually smaller in value than the right child, that is equal to 4. So we'll copy this particular element here in the parent node. Okay, we'll copy uh, this particular left child value into parent node, its parent node. Okay, so that is why the arrow shows that out of 2 and 4, 2 successes to the parent node. Similarly, in this case, out of 6 and 10, 6 being the minimum value out of these two, 6 will move ahead and will be copied to the parent node. Okay, similarly, in this case, out of 1 and 7, 1 being the minimum, 1 will move ahead to be copied in the parent node. And similarly, in this case, out of 3 and 8, 3 being the minimum will move ahead to be copied into the parent node. Now, we have decided the level after, sorry, we have decided the level after the leaf node. What would be the values in this particular level here? So 2, 6, 1 and 3 are the candidates for the first non-leaf level if we are counting from the bottom to up. Okay, now we have to fill the subsequent levels as such by laying the idea of minimum heap. Now again, as we know that these two positions will be initially 0 and including this, so the minimum of these two values, that is the left subchild of this particular node 2 and the right subchild of this particular node, that is 6, the minimum of these two will succeed and will be copied to the parent node. Okay, now out of 2 and 6, 2 being the minimum will be copied again to the parent node. So you can say 2 will succeed out of these two and move towards the root. So it is, you can see that we are basically moving up towards the root of this binary tree, from the leaves towards the root, and the successors are defined or are decided on the basis of their minimum, on the basis of the values, that is the minimum of the two childs will succeed. So out of 2 and 6, 2 being the minimum value will succeed to the parent node. And similarly here, from 1 and 3, 1 being the minimum will succeed to the parent node. Now again, minimum heap ideology will be implied here in this particular tree, subtree here. That is, the root of this particular complete tree is going to be filled on the basis of the values of these two childs. Okay, now the minimum of these two, the minimum valued child of these two will succeed to the top or to the root, not the top but to the root. So out of 2 and 1, 1 being the minimum value will succeed and will be copied to the root node. So as you can see, by this is actually the one pass. You can say this is the one pass of our tournament sort. By one pass, by implying the one pass, we have actually found out the minimum value of the complete array. The minimum value of the complete array. Okay, sorry, minimum value of the complete array. As you can see, 1 being the minimum value of the complete array. So we'll take this out and store it in a different list or an array. Okay, so one element has been sorted, the minimum value has been sorted, it is going to be inserted at the beginning of the array. Now if we go on like these, for the second element again we have to sort like this, and for the third and fourth, and then this particular sorting algorithm would not be of much difference than your linear search. So the beauty of this tournament sort is the tournament sort actually remembers what were the results of the previous tournament. Okay, why I'm saying tournament? Because the tournament between 2 and 4 actually results in a winner, that is 2. The tournament between 6 and 10 actually results in a winner, that is 6. So it remembers the tournament results. Now after removal of 1 from this tree, we have to remove all the occurrences of 1. That is, we'll remove 1 from here, we'll remove 1 from here, and we'll remove 1 from here and also 1 from here. As we have applied the ideology of minimum heap, so instead of this 1 in the leaf node, we will insert a value equal to infinity. because in that way we will be sure that if we compare any element with infinity, the element will be always be of minimum value out of these two. So that element will always go to the top. Okay. And as tournament sort remembers the results of the last tournament, this will not be disturbed. So 3 is already there. And this element 7 will succeed because instead of 1 we have now infinite here. And this result here, this tournament here is as it is because tournament sort remembers and nothing has been removed from here. So out of this tournament, 3 will succeed. Out of this tournament, 7 will succeed. And out of 7 and 3, 3 will succeed. And then this 3 will be compared with 2. And this time, 2 will go to the top, and we will actually remove it and store it in the list. Okay? So I'll show you in the next slide what I'm trying to say here. As you can see, these three values, that is this 2, this 3, this 7, and this top is actually now vacant. Okay, we have not vacated these positions, we have not changed these positions because tournament sort remembers these tournament results. That is why I've written here the results unchanged in this half, because the value that has been missing from the last tournament is 1, and 1 has nothing to do in this part of subtree. Okay, so 1 is missing from here, 1 is missing from here, 1 is missing from here, 1 is missing from here. Now here, instead of 1, I will insert infinity. Please pardon my symbolism, it is not infinity, but this is what I mean actually. So out of infinity and 7, 7 will be the minimum value, it will move ahead. And we have tournament sort has remembered this particular result here. So out of 7 and 3, 3 will move up, and out of 3 and 2, 2 will move up this time, and I will remove this 2 from the list and store it after 1. So we have a second candidate. The second minimum candidate of this array will be now inserted into this list. So as you can see, we don't have to go through the entire process again. All we have to do is just remove the last winner from the tournament and remember all the previous results, and just replay those tournaments in which the last winner is involved. Okay, so we have replayed the tournaments like this tournament here, this tournament here, and this tournament here only. Okay, all the other tournaments, that is this one, and this one will stay as it, because there is no way of playing them again. These games cannot be, there's no sense in playing them again, because out of 2 and 4, again 2 will pass, move ahead. Out of 6 and 10, 6 will move ahead. Out of 3 and 8, 3 will move ahead. Okay, so now at this time, at this second pass of your tournament sort, 2 will be the winner. Now 2 will be here, and as in the next slide, the position of 2 is vacated, and instead of 2 we have inserted infinity here. Now out of infinity and 4, 4 will be the winner, it will pass ahead. Out of 4 and 6, as you can see now, this particular right subtree of with respect to root is now unchanged. Okay, we have not changed it. So tournament sort remembers these games, the result of these games. We have only changed this particular subtree. Why? Because 2 has been removed and 2 is involved in this half of the game. Okay, also not complete this half, only this half. So out of infinity and 4, 4 will move ahead. Out of 4 and 6, 4 will move ahead. And out of 4 and 3, 3 will move ahead. So this time 3 will be removed out of it. And instead of 3 here, we'll list infinite. And out of 7 and 8, 7 will move ahead. Okay, and out of 7 and 4, 4 will move ahead. So 4 will be there after 3. So in this way, your list will be sorted out. So in that way, you can say that in the tournament sort, all we have to do is just apply the idea of minimum heap and remember the last results. Now it is easy saying that than doing. How can we achieve this in our computer systems? Now we can do this by the uh, using the formulas of your complete binary trees. By the meaning of that, I want to say that in the max heap or in the heap sort, we have seen the formula uh, from where the if we know the number of leaves, or you can say from where you can start the or you can find out the non-leaf nodes. What would be the greatest index of your non-leaf nodes? That is from where your non-leaf nodes are starting in the array, and below that index you have to store all your array elements. So what I have done here is, we have first stored all the arrays of the all the elements of the array to be sorted in a larger array. We can find out the this value of larger array, the length of this larger array, by using the formula for the complete binary tree. That is, if you have the number of leaf nodes, you can find out the value of this, the length of this complete binary tree. Okay, or you can say the how many number of nodes in this complete binary tree. So as you can see, if you have the index of the last leaf node, you can find out the index of your last non-leaf node. That is 7. We have seen this formula in the heap sort. If you don't remember it, please go through that lecture also. Now, what we'll do here is, let me show in the next slide. This is actually how it is going to be done in your system. So last and second last will be compared and will be stored in the first non-leaf node. The result of that, the result is based on the min heap. Out of third last and fourth last, min heap will ideology will be employed, and the result will be stored in the sixth, that is second last non-leaf node. And similarly, out of 6 and 10, 6 will be stored at the fifth index, and out of 2 and 4, 2 will be stored at the fourth index. Okay, then again, the elements 1 and 3 will be compared with the with respect to the ideology of minimum heap, and the result will be stored at the third index. And similarly, out of 2 and 6, 2 will proceed to the second index, and then again out of 2 and 1, 1 will proceed to the first index of the array. Okay, so first place, second place, third place, as you can see that this is like a tournament. This is like your ICC World Cup. This is how we proceed for the finals. Okay, this is your final match between 2 and 1. This is your semi-final matches between 2 and 6 and 1 and 3, and these are your league matches. So I think you will now see the ideology why we call it the tournament sort. When this first pass, this is actually your first pass. When this first pass is completed, you will see you have a clear winner. That is one. Now we'll remove this, and as we have removed this, we have to remove all the occurrences of one. That is, one will be removed from here, one will be removed from here, and one will be removed from here at the 12th index. And instead of that, we'll store infinite value or a very large value, which you are sure that your array or the elements you have to sort is not going to reach at that particular threshold. Okay, so we'll remove that. And how we are going to remove these values? All we have to do is attach a pointer to each of these values. Attach a pointer for each of these values. Let me show in the next slide. Yeah, attach a pointer to all of these values. So you can see here we have attached a pointer for the 8, that is 15th. For 3 it is 14th. For 7 it is 13th. For 1 is 12th, 11th, 6th, and as these values make occurrences at the third level, second level, and first level, these pointers remain unchanged. So all you have to do is just remove the values at these levels. That is, if I have to remove one, then all the elements which have a pointer equal to 12 will be removed from the this particular array and will be replaced with infinity. And then again we have to make a pass, and on the basis of that pass, a new winner will be at the top. Okay, a new winner will be at the top, and this is how we have to repeat this process until all the elements from this particular array are removed. Okay, and that is how you will have a sorted array, that is from the lowest value to the highest value in the new array in which we are going to which you are actually let's say storing the values. So this is a tournament sort. I am not going to provide you with the algorithm. The algorithm is a bit tricky, not even tricky, but it's too long. And I would suggest you to explain this particular tournament sort in the way that I have suggested, that I have shown you here, with the help of these let's say graphical, the tree, pictorial tree representations and this array form, it would be best to, it will also going to save your time in the exam, because it is not going to come for more than 10 marks. And it will be better if you do that, because you have to attempt all other questions also. Okay, so thank you.